Hello and welcome to Mann's Model Moments. Let's clear up some myths about acrylic paints. I cringe whenever I hear people say things like, well, Tamiya paints aren't really true acrylics because they're alcohol based, or acrylic paints are water based. For the record, both of these statements are completely wrong. Anyone who says them should not be listened to with regard to any advice they attempt to give on the subjects of paint. Stop listening, walk away. So what is acrylic paint? Where has this myth about them being water-based come from? And what on earth are Tamiya and other non-water-based acrylics? At its most basic level, paint consists of two main components, a pigment and some sort of carrier medium or vehicle. This is what makes it different from a chalk or pastel after all, that liquid nature. So with that as our baseline, let's start with some history. Some of the first ever paints were ochres, a naturally occurring clay pigment that could be mixed with water and applied to form paintings. The oldest of these that have survived to the present day, in caves throughout the world, date from around 100,000 years ago. The problem with a pigment just applied in a solvent in this manner, however, is that once it is dried, application of more solvent can wash the pigment off. To prevent that, you need some form of binder, something to trap the paint on the surface. Simple water-soluble pigments often rely on the porous nature of the substrate, the paper or cave wall, to trap the pigment, but that's not very effective. Humans, however, are nothing if not inventive, and we have surviving evidence from about 5,000 years ago of various ochre pigments that had animal fat, milk, or eggs mixed into their carrier medium as a binder. This is really when paint evolved into its holy trinity of pigment, binder, and diluent or solvent. Eggs were often used as a medium for thousands of years after that time, since they adhered to the surface, dried to a hard finish, were very durable, and could be diluted with water. The main problem with them being that the paints dried quickly, but they took weeks or even months to cure. The earliest record, however, of oil-based paints goes back to the late Roman Empire, but it wasn't until around the 13th century that oil-based mediums started to become more widely used for their more vibrant preservation of their pigment's colour. Oil paints use the air oxidation of oils, which takes a long time, allowing a painting to be worked on over a long time with ease, but again, taking a long time to fully cure. The other factor here is that during all of this time, paints had to be prepared by the painter prior to their use, grinding pigments and adding medium to the right consistency before they painted. Even during the Industrial Revolution, paints were still supplied as pigments that could then be mixed for use by the end user. It wasn't until the end of the 19th century that a US-based company made the first paint ready to use straight from the tin. What we generally now know of as enamel paints are what is known as alkyd-based, generally a polyester resin created by modifying fatty acids like that linseed oil used for oil painting. These still remain the dominant resin binder of commercial solvent-based coatings available worldwide today. They take less time to dry than traditional oil paints, but still usually around a day, and they importantly still rely on mineral spirit solvents, making them messy and unpleasant to use and to clean up. Now, although initially invented in Germany during the Second World War, it was the post-war shortage of linseed oil which spurred on the proliferation of the artificial resin paints that we now know as acrylics. These combined some of the durability of alkyd and oil paints, but with much faster drying times. The first acrylic paints were also mineral spirit based, but emulsion-based artist paints followed shortly after in the 1950s. Let's have a look at what a paint is again. A pigment, a binder, and a solvent. The pigment gives us our colour, the binder holds the pigment and sticks it to the surface, and the diluent or solvent gives our paint its fluid properties. If we look at those ancient egg yolk based paints, the binder is the egg yolk, a complex, sticky mix of biological molecules. These were mixed with pigments like ochre or ground metal compounds like red lead, and diluted with water mixtures as a solvent to a consistency that could then be painted with. Later oil paints substituted the egg yolk binder for linseed oil, which polymerizes as it dries, trapping and adhering the pigment to the subject. The solvents used were other lighter oils and mineral spirits like turpentine. Alkyd paints then took that linseed oil and chemically modified it to create a resin, something that would polymerize faster than the oil itself, and we have the polyester binders that are the backbone of enamel paints, but the solvents are still mineral spirit based. In acrylic paints, the binder is acrylic, which also polymerizes to create a hard, resistant finish. The important thing here is that it happens much faster than with natural oils, but as we've seen, they were originally based on mineral spirits before being water soluble, and we know Tamiya paints contain alcohols, so what's going on here? Let's take a closer look at some of those individual components in acrylic paint again to understand things a little bit better. Today we have a huge range of pigments, and it's worth talking a little about them because they'll come into play later. Broadly speaking, pigments fall into one of two categories: inorganic and organic. Looking at inorganic pigments, these tend to be the sorts of things that you can dig out of the ground, minerals, or from the sort of hard chemical production you might expect to process those mined materials. That means that a lot of them have been in use for a very long time. They often contain relatively simple metal salts, which means they're often fade resistant, and as they're often mined or made in bulk quantities, they tend to be fairly cheap. On the downside, they are sometimes less vibrant than organic pigments, and they can be quite toxic. Let's have a look at some of the main colours to see that. Our first example is cinnabar, one of the oldest known pigments mined from volcanic regions for thousands of years, possibly as far back as the Neolithic. It is a simple sulfide of mercury, and it was mined by the Romans both for use as a pigment and to produce quicksilver, mercury metal. Obviously, being a mercury compound, it is neurotoxic, something those same Romans recognised over 2,000 years ago. Moving to yellow, we have orpiment, another volcanic mineral named from the Latin auri pigmentum, meaning gold pigment. It's a water-soluble sulfide of another poisonous element, this time arsenic, hence its other popular name. Again, it has been used for thousands of years all over the world up until the 19th century, when other yellows and its extreme toxicity made it fall out of use. For green we have malachite, another ancient pigment in use for at least 6,000 years. You may have seen malachite as polished stones that you can buy in museums or gift shops, as it's a carbonate hydroxide of copper, making it much safer than our prior examples. My blue example is Persian blue, formed from crushed lapis lazuli, the primary pigmented mineral of which is lazurite. This is actually a group of blues and a bit more of a complex mixture, and it shouldn't be confused with lazulite, which contains magnesium and iron in its crystal lattice structure, rather than the sulfur-containing silicate mineral lazurite is. The last two examples I'm going to give you are unlike the previous naturally occurring mineral pigments, as they are both produced industrially and are both related, but they're very different pigments. The first of these is titanium white, titanium dioxide, which although occurring naturally is also one of the most industrially produced pigments on Earth, more than 9 million tons of it each year. It's used in a lot of paints to brighten them because of its high refractive index and to make them more opaque. You'll find it's added to more colours than you might expect, as well as in other applications like toothpaste, sunscreen and even food additive. Look for E171 in foods. That's titanium dioxide. Just to flip things on its head, I'm now going to go to the other end of the spectrum from white to black. No, you're not reading that incorrectly. Titanium black is also titanium oxide, but with a little higher ratio of titanium to the oxygen. The crystal structure here makes the compound absorb light rather than reflect it, just showing that tiny changes in chemical and molecular composition can have dramatic effects on the resulting pigment. So that's inorganic pigments. What about organic pigments? Well, this has nothing to do with sustainably growing potatoes or even plants for pigments, but rather organic chemistry, which is really the chemistry of carbon, the properties of which allow extremely large and complex molecules that allow life as we know it to happen, which is what the name alludes to. Now, organic pigments have some great benefits over inorganic pigments, in that they can produce great colour tones and depth. That does come at a price though, as the majority of organic pigments are more expensive than inorganic-based equivalents. They also have a varied amount of light fastness, meaning that they can fade or change over time. They generally tend to be more recent than inorganic pigments, though not always, as our first example will demonstrate. That first example is alizarin red, which is a pigment extracted from the roots of various rubia species, otherwise known as madder plants. These were cultivated from antiquity specifically for use as dyes for cloth throughout the Old World. The roots contained an anthracene compound responsible for the coloration. Moving to yellow, and we have areolide yellow, which are really a family of yellows which have partially displaced the more toxic cadmium yellows that in turn had replaced the extremely toxic orpiment that we saw previously. These are semi-transparent pigments and have been produced chemically over the past century. Looking at green, and I wanted to show that although generally less toxic than inorganic pigments, it's not always the case, and certainly not here with Paris green. This was a very popular colour used extensively by many famous 19th century Impressionist painters such as Monet, Gauguin and Van Gogh. It was also employed as wallpaper pigment, in book bindings, as an insecticide and even to kill rats, but its high toxicity saw it withdrawn for safer alternatives. Next I've chosen the widespread phthalo blue, a synthetic pigment commercialised in the 1930s and available in different shades from differing isometric forms. One point to note here is that early in its development it was difficult to create a stable pigment when mixed with titanium dioxide, a point to remember and that we'll come back to later. Now there aren't really great examples of organic white pigments, mainly because there isn't the need for them, but there are great organic black pigments, stemming from carbon itself. Native carbon is of course black, and there are plenty of things that can be burnt to produce it. For pigments, the carbonaceous material is incompletely burned, leaving some trace materials in the structure which help with other properties. The formula here is generic rather than absolute. The exact formula will vary depending on the source material and the level of combustion. So my point in all of this was to demonstrate the extremely wide range and importantly chemistries of pigments available for us today, with more being created as we carry on. Importantly for paints though, as I've alluded to in several examples, to get the colour we need for any given paint, it's actually a blend of pigments. This is not necessarily as easy as it seems. Pigments may interact with each other in unwanted ways, as with the early phthalo blues and titanium dioxide. Paint manufacturers need to consider costs and blends and 100 other things in order to create the perfect shade for their paint. They also need to consider how these pigments will affect the chemistry of the solutions they disperse them into, and we'll return to that later. As I mentioned in the history, the binder is the glue that sticks our pigment to the surface we're painting and keeps it there. For acrylic paints, that's acrylic resin polymers. This is what makes our paint an acrylic. The paint derives its name from the binder. The two are appropriately bound together. You may also be used to hearing acrylic in other terms though, by other names like perspex or plexiglass, or maybe in acrylic nails, and you'd be perfectly correct. All of these materials derive primarily from polymers of this, methyl methacrylate. This is the monomer, the individual building block unit of the polymer. The polymer is created when two molecules break their double bonds on their terminal carbon to join together. Other molecules can then get in on the fun and do the same thing, causing a cascade reaction, polymerization, where long chains of monomers join together in strings up to 10,000 units long. These don't just sit in long lines though, they tend to clump up, and of course they can get wrapped up with other chains, and this is how we end up with solid blocks. Now one of the beauties of this sort of reaction is that it's not just limited to methyl methacrylate. If we have other acrylates, we can do the same thing with those, and this is the case in reality. Common acrylate monomers used are butyl acrylate and ethyl acrylate. As you can see, these all have the same group that we just did the polymerization reaction on at the top, with a similar structure below, and just differing in the length or branching of the molecule downstream. In paints, polymers made up of ethyl acrylate and methyl methacrylate were actually used first, but gave way to other polymers because of superior properties such as strength. Ironically, the relative weakness of ethyl acrylate polymers have led to its increasing use in nail treatments, since MMA fixed nails tend to be too strong, meaning caught nails could actually result in lifting of the nail bed rather than breaking the nail. For painters though, improved strength is good, so a polymer created with a mix of methyl methacrylate and N-butyl acrylate works perfectly. Now, as you might have guessed from the long chain hydrocarbon nature of these molecules, or from the smell of anyone having acrylic nails done, none of these compounds is water soluble in any significant way. In fact, if you remember from the history section, the first acrylic paints were solvent based, so how can we have this reputation of acrylics being water based? If we actually examine acrylic polymers under an electron microscope, we find that several hundred of these long chains come together to form submicron sized spheres. What we do to make acrylics water soluble is to introduce a surfactant. Think fairy dish soap and you won't be far off. Surfactants like this work by having a hydrophilic, water-loving or water-soluble section or head, and a long hydrophobic, that's fat-loving or organic solvent-soluble tail. This is how detergents clean things, by making fats or other water-insoluble dirt able to be washed away with water. They form a bridge between the two immiscible components. Our surfactant can thus surround our submicron-sized acrylic spheres and create a mixture known as an acrylic emulsion that is the base for our water-soluble paint. That neatly brings us on to our next paint component, the solvent or diluent. So we now have two distinct possibilities for our binder, what I'll call native acrylics, which are miscible in organic solvents, and then acrylic emulsions, which are miscible in water. Looking first at our native acrylics, these are what people generally refer to as lacquers. Outlaw paints, for example, are what most people would term acrylic lacquers. They use an acrylic binder in its native state that can be mixed with a variety of organic solvents. Historically, these have been organic solvents like toluene, isobutanol, methyl ether ketone, and amyl or butyl acetate. With increasingly strict laws on volatile organic carbons, or VOCs, these are often being reduced in favour of a high proportion of acetone. If a lot of these are ringing bells for you, it's because many of these can also be used as plastic cement. Methyl ether ketone, butyl acetate and acetone are all common ingredients of them, and why you can often use lacquer thinner as polystyrene cement, because the polymers of polystyrene are also soluble in them. For water-soluble, acrylic emulsion-based paints, the solvent is easy. It's water. That's one of the primary advantages of having this advancement after all. But wait a minute, Alex, I can hear you saying behind your monitors, phones and TVs. What about Tamiya paints? They're not water-based, they're alcohol-based. Well, they're not. Firstly, this is why words are important, and the whole solvent-based or water-based and so on is a misnomer. It's more accurate to say what the paints are miscible with, what they will mix with, and Tamiya paints mix with water, and they are more water than solvent. Secondly, let's have a look at what else is in Tamiya paint. A quick rustle up of the MSDS, and we can see that they contain 4 major solvent components, as shown here. Now, a couple of these are very familiar to us. Ethanol, or ethyl alcohol, is the name for the alcohol many of us consume in beer, wine or spirits. Propan-2-ol is the scientific name for isopropanol, or rubbing alcohol, which many of us have used extensively in our hobby for years. That leaves these 2 scarily named things at the top. But if we take a look at the names, there's a clue here. They both end in -ol. That refers to this OH functional group attached to the carbon, and it indicates that these are alcohols or alcohol derivatives. In fact, looking at the names, you can see we have alcohol names in there. Our first component, in fact, has the same propan-2-ol name in it. I can change the orientation of the isopropanol molecule around so it has roughly the same orientation as the first compound, and here I've highlighted what has changed. So instead of a hydrogen atom, the first compound has this oxygen linking another carbon with 3 hydrogens on it. That carbon and 3 hydrogens is known as a methyl group, and because it's connected through an oxygen, we can shorten that to methoxy. The numbers just tell us which carbon atom it's stuck to. Knowing that, we can also see our second molecule has a methoxy in the name, and we can see the same structure. So, although we've not looked up any of these things on Google yet, we can already see that they are a pretty closely related group of chemicals. Now, delving further into the MSDS, we can see how much of each of these is in our paint, and looking them up on any chemical database can show us one important factor: their water solubility. Our isopropanol and methoxy isopropanol are making up the majority of the solvent content here, and both are fully miscible with water. That means that no matter how much you add of one to the other, they're fully compatible. We've a little bit of ethanol, which as we all know is fully miscible with water, and then just 3% of our last component, the methoxymethyl-butanol. This is soluble in water up to 100 grams per litre, or 10%, approximately, as this is weight per volume. As we only have 3% of this in here, then it doesn't matter how much we dilute this in water, it's always going to be miscible. So this tells us our Tamiya paint is fully water miscible, which should be of no surprise to anyone, but I'm sure some people will be frowning at this, and I'm sure there's going to be at least one person out there that says, "But wait Alex, I've a gotcha. Tamiya paints are soluble in Mr. Colour thinners, so they can't be water miscible." Well, I'm sorry, but this just shows you don't understand chemistry at all. You can actually mix pure water with Mr. Hobby thinner and levelling thinner to about 20 or 25%. A lot of the solvents in Mr. Hobby thinner are very versatile and have wide solvent miscibilities, although some of them, like isobutanol, aren't very water soluble, when in a complex mixture, as these thinners are, they can be quite tolerant. Ethanol, good old drinking alcohol, and isopropanol are two very good examples of solvents with wide miscibilities. It's the reason isopropanol is used so much. Ethanol is arguably a better solvent, but because people can drink it, with only minor side effects, means all the laws and regulations we have around it, which make it more complicated legislatively to use, and more expensive since it can also attract duties. Acetone is another one, so don't think that just because something is water miscible, it can't also mix with traditional organic solvents. Now the last things we can have in paint I've labelled under one banner as other stuff. These are wide and varied, and a lot of them are specifically down to water miscibility. Before we get to that, however, there are a few additives that both solvent and water miscible acrylics can have. The first of these is plasticizer. This basically helps the paint be more flexible, or plastic, and helps prevent cracking of the paint as it's drying. Another way to sometimes help that, especially in solvent-based acrylics where drying times are very fast, you can have a retarder. These tend to be solvents with similar miscibility properties, but a lower volatility, leading to longer drying times that allows the paint to settle better before the solvent evaporates. The last additive, which can be equally applicable to both solvent systems, are UV inhibitors. These are compounds that absorb or otherwise deflect the damaging effects of UV radiation on a paint to improve its long-term appearance. We then come to the complexities added by using water as a solvent. This is because, as I've mentioned on some live streams, water is weird. Dihydrogen oxide is a very unique substance. We don't think about it because it's an everyday and common thing, but it shouldn't really be how it is. Water has a mass of 18 grams per mole and is liquid at standard temperature and pressure. Its molar mass is much less than that of carbon monoxide or dioxide, both of which are gases, and the lightest equivalent metal oxide is dilithium oxide, which is a solid. In fact, virtually all oxides in the periodic table are either solids or gases. Unlike most of the compounds known to us, the solid form of water is less dense than its liquid form, meaning ice floats on water rather than sinking, as almost everything else does. A simple molecular model of water gives us a clue as to what's happening, because as you see here, the two hydrogens aren't sticking out equally, they're bent to give the molecule this little V shape. We also have an uneven charge distribution over that V shape, making the pointy end a little negative and the other sides a little positive. Overall, the molecule is neutral, but this regional charge, like the poles of a battery or magnet, lead molecules like this to be known as polar. Organic solvents, like the toluene we mentioned in lacquer thinners earlier, generally have no such charge distribution, so are known as non-polar. This polar nature of water makes it a great solvent for ionic compounds, such as salt. Non-polar solvents like gasoline tend not to be so great at that. As well as this polar nature, hydrogen atoms bound directly to certain atoms, oxygen being one of them, can form what are known as hydrogen bonds. Without getting too sciencey, this effectively makes water sticky to itself and is responsible for its many unusual properties, including its very high surface tension. This allows things like water boatmen to use to skate around on, and, importantly for us and our paint, it also allows it to bead up. This is not something we particularly desire in our paints. High surface tension is in fact our enemy. This is where a whole category of additives can come in, which I'll generally call flow improvers. In reality, what these are doing is lowering the viscosity of our paint mixture or reducing its surface tension, and most frequently both. This can be achieved in a couple of ways. The first of these is to add a miscible solvent that has better properties. This is effectively why Tamiya's water-soluble paints are easier to spray than many others, because they already have a large percentage of water-miscible alcohols in them, as we've already seen. The second way is to add some sort of surfactant. Once again, think a detergent, like fairy liquid, and in fact you can thin some paints with mildly soapy water without issue. The problem that can lead to, of course, is unwanted bubbles or foaming. To deal with this latter problem, the formulator can then add an anti-foaming agent, typically some sort of silicone-based agent. This suppresses the formation of bubbles in the paint mixture. The next thing we potentially have to deal with comes from our pigments. With water in the mix, some of our pigments may dissolve and change the chemistry of the overall mixture, making it too acid or alkaline, for example. Other pigments may only be soluble or the correct colour at certain specific levels of acid, base or neutrality. To stabilise all of this, we may add a buffer compound, which effectively absorbs small changes in the local environment to keep things at a certain specific range. Now of course, the other thing that water also allows is life, and now we have a nice complex soup, we need to prevent bacteria and other microorganisms from breeding in there, so we can add some antimicrobial agents to the mix too. Now that's a lot of extra stuff, but I guess the million-dollar question about all of this is, so what? So let's talk a bit about that in how we actually use our water-miscible paint. Okay, so we've got our complex chemical soup in a bottle, which a company has gone through extensive research and development to finely balance the 20 or 30 or more individual components to get this colour-fast, water-soluble paint that dries quickly, has vibrant tones, doesn't crack and won't go off. You take this magnificent blend that you'd parted with £2 or £3 to own and dilute it with water. And by that of course I mean high quality deionized water, right? Right? Or do you mean whatever stuff came out of whatever tap you happen to find near you? Because if it's the latter and you're complaining, then you have some soul searching to do. Depending on where in the world you are and at what time of year and the recent weather, the hardness of your water can vary from very soft to very hard. Although this is measured as the total dissolved solids, one of the most important and well known of these for us is calcium carbonate. These are all sources of calcium carbonate, and do you notice one commonality? None of these looks particularly soluble in water. They all look a bit like rocks. Calcium carbonate is, of course, not very soluble in water at all, 30 milligrams per litre. And of course, it likes to come out of solution as soon as it possibly can. We all know this from boiling our kettles or having to descale the washing machine. Exactly the same thing can happen if we add hard water to paint. Another consideration is pH. This is related to hardness, as hard water tends toward high pH and soft water tends towards acidity, but again, this is not what a paint manufacturer has necessarily envisaged. You may be in a soft water area, but if you have acid water and you add it to your paint, it can upset that delicate balance that those formulators pulled their hair out creating. Even if you are using deionized water, remember that when you add 1 volume of water to 1 volume of paint, you're diluting all of those additives by half, so they're going to be doing half as good a job. You dilute any paint enough and its properties will break down. Here's an example. I've taken Army Painter Dragon Red here for the lower fuselage half, and Tamiya XF7 Red for the upper half. In each case I've brush painted with neat paint, then I've thinned it 1:1 with pure water, painted, thinned that solution 1:1 and so on, giving me a serial dilution. You can see in both cases the paint is covering the plastic, and as it is diluted, its ability to wet the plastic surface is overcome by the surface tension of the water. I think the Tamiya paint does a better job initially, probably because even 10% solvent is helping, but then it does seem to reach a critical threshold. For this second test, I've used airbrush thinner to preserve more properties of the paint. You can see it produces a much more even spread of the highly thinned paint, though at the lower dilutions the properties of the thinner are not helping the paint on the extreme curve of the aircraft nose. Using thinner on the Tamiya paint gives a much better adhesion to the plastic, resulting in a more even spread of pigment even at the high dilution rates. So what have we learned from all of this? Well, I hope that if nothing else, you come away knowing that fundamentally paints are a mix of three components: pigment, binder and solvent. And that in acrylic paints, the binder is acrylic polymer. The form that acrylic is made in will dictate the choice of solvent, so saying a paint is water-based or solvent-based is not accurate and not particularly helpful. It's the choice of the binder format that is most important. Choosing a more native acrylic polymer allows the use of more traditional organic solvents that provide good wetting and spraying characteristics, allow generally simpler formulations, but come with various unpleasant issues primarily from their VOCs. Use of an acrylic emulsion, on the other hand, allows the use of water as a solvent, but also generally more complex formulations to deal with the peculiarities that water brings from a physical and chemical point of view. The great upside of all of this, however, is that acrylic-based paints are probably the most diverse type of paints ever, with formulations continuously evolving and improving. Their versatility, colour range, durability and ease of use has made them ubiquitous throughout our lives. From painting our houses, spraying the cars we drive, to what we paint on our hobby benches. I hope you appreciate that small glimpse into the very complex world of paint chemistry and how understanding it even just a little can help us respect it and also get better results. At an absolute minimum, I hoped it stopped those of you that were going to put your foot in your mouth and look like an absolute fool when you tell someone that Tamiya paints aren't proper acrylics because they're not water-based. That's all for this instalment of Mann's Model Moments. If you enjoyed the video, please click the like button, subscribe to the channel for more like it, and share this video with others you think would also enjoy it. You can also follow me on Instagram, Twitter and Facebook, and if you're feeling generous then I also have a Patreon, which is absolutely the best way of helping me to grow the channel and produce more content like this. With that, I hope you have plenty of modelling moments of your own, and I look forward to welcoming you on the next video.